Hello everyone. Today I'm going to show you how to find your location using celestial navigation. Only with one star observation, not two, not three of course, and also without a map. So how can I find my location without a map? It's by using the geometry of the world that we live in, which is a sphere. I'll be using the geometry of the globe or the sphere. The first thing, we will start by having a quick look of the Nautical almanac, because I need information from there. Then I'll show you how I use these information, how to analyze and produce what equations or what geometry to bring my location. Let's have a look at the Nautical almanac. Every day has or every 3 days has 2 pages, and this is the page that I'm interested in, the page that shows the ground position or geographical position of Aries every hour. You start from 0 until 23, so you get that this 0 hour is 24, like 1 minute after midnight, and this 23. And I assume if the difference is 15 degrees between each hour and the next, then maybe you can work it out. But for simplicity, I'll be just using the head of the hour. Now we have here, these are the stars that we use for navigation, the 50 something stars. All right, so how do I get the ground position of these stars? What we have here is the shift between the star ground position and Aries ground position. So Aries is the reference point. So I thought to give a deeper look into using the stars from the Nautical almanac to get the GP of a star. So first thing we have is how many longitudes from Greenwich line to Aries longitude, and that changes every hour. All right, so, and then there's a constant value between Aries to the various stars in the Nautical almanac. Like in this case, the star Vega is around 80 degrees to the west of Aries. Now, as you see, if we do the math, we get the longitude from Vega to the Greenwich Mean Time, or the Greenwich line. In this case, you don't see Vega, of course, but maybe right here you can barely see Vega. So now you know the longitude of Vega, and also it has a constant latitude, so you are able to use the elevation angle and put the circle of equal latitude. So here's the Excel Nautical almanac for 2021. What you do is just you put the date here, let's say 15, and you can see that the ground hour angle for Aries changes for every hour. Then I added the sheet here, this one, and from this point I can get the angle, the GHA of Aries from here, and then this is for Vega, and then automatically when I change the date, the star GHA of Vega, for example, changes. Now let's go into how did I do it. So here's the spherical Earth, and here is my position. All right, so after using the Nautical almanac to get the ground or the geographical position for a star that I already observed with an elevation angle and azimuth, this is the ground position for the star. And as you can see, I just made a polygon to represent the line from the GP to the star. Then here in my location, I'm standing on a plane, or the plane I'm standing to that is tangent to the Earth where I'm standing, right? So this is the plane, and as you can see, it's square. I try to make it as a square or rectangle. So these lines are parallel to my longitude line, and these lines are parallel to my latitude line. Now, of course, because I've made this very large, it's not parallel in this point and this point, but what I mean at the center here, they are parallel, and here in the center here, they are parallel to the longitude. So this is my plane. Then there's also a plane for the GP. So now we have these two planes. We have a line of sight, or a line that's perpendicular on one of them, and from my position to the star, the line of sight is parallel to that line. So if I smacked those two planes with two lines, the line of sight and the line from the GP to the star, then I'm going to get some information. So let's go and see that. So here's the blue plane, right? The blue plane where this pole is perpendicular to. And this is the green plane. This is where I'm standing on. And as you can see, it's very obvious that the yellow pole, is, what the hell, is perpendicular on the blue plane. But for me, on this green plane, the same pole is not perpendicular. This is my line of sight to the star. So now we can see that this is my azimuth from the north. Yeah, I forgot to add something, that this is the north direction for the blue plane. So this is my azimuth here, and this angle is 90 minus my azimuth. And if we analyze, we get this triangle, right? This is perpendicular on the green plane. And this, if I look like this is perpendicular, or not perpendicular. It's the line of sight parallel to the Earth axis. This line here represents a line parallel to the Earth axis. So I'm not going to go deep into the geometry, but I'm just saying that it's the main rule when you're trying to work 3D geometry is that you look at triangles from different perspectives and you start to analyze them. Like, for example, if this length is 1, when I'm looking at it from this perspective, it is not 1, it is less than 1, and I can calculate it because I know the latitude of this blue plane, so I know the orientation of this yellow line in relation to the Earth axis, so I can get its length from this perspective. And since I know the length, let's suppose that its actual length is 1, I can get also the length underneath it, and the length on the along the latitude lines here, this length and this length. Yeah, so that's the main idea. Now let's go into testing the math that I worked with. So here's the test setting. I choose June, the 2nd of June, because on that day the star Vega is opposite to the sun. That means that from my location here in Egypt, I can move east and I can move west a lot without having to deal with the sun. So as you can see here, the longitude, latitude is 30 and 30. So let's just put the angles here. The elevation 81, 8 and 0.3 the azimuth 3533142.3, and there is the longitude and latitude. Right, so now let's go to another location. Let's increase, let's go a little bit south. And funny, this motion, when you're going away from the north, you would see the same motion of the stars if you're in the southern hemisphere and moving away from the south. Let's go a little bit to the east. Oh no, not this, sorry. That's the west, but it's okay. Yeah, that's fine. Now let's bring our Excel sheet. From this location, the altitude is 4338.8, the azimuth 432847.6, and as you can see, 9 latitude 0.005. Here it is 9, right? And the we are west by 11, and that's why we get the negative here, negative almost 11, like 7 in 1,000. That's less than, I don't know, I can calculate it, but you get the idea. Let's go to another location to the east. Right, that's enough. And we get the readings: 38 degrees 19 minutes 59.5 seconds, 313 07 minutes 34.6 seconds, and you get 9, yes, that is 9, and 76, yes, 76 point something. So there you have it, finding your location using the stars and the geometry of our world, the sphere. So I think from now on it's very silly to say that celestial navigation doesn't work on a globe, and even more silly to say that it works only on a flat earth. So thank you all for watching until now, and see you on the next one.